Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, Illustrations with the R software. We're in chapter 4, part of this playlist that I'm calling Joint Distributions. And let's jump to today's topic, which is transformation of random variables. Now, specifically, it's transformation of bivariate random variables. And let's let x and y be continuous random variables. They have a joint density f of x, y. And let u and b be random variables defined as functions of our bivariate data x and y. So that's what g1 is, a function of x and y, and that's u. g2 is a function of x and y, and we call that v. And g1 and g2 are one-to-one transformations. So let's let the inverse transformation be defined like this. So x and y, under that inverse transformation, each are functions of the bivariate data u and v, and h1 the function of u and v is x, and y is h2, which is a function of u and v. Now we're going to assume that h1 and h2 have continuous first partial derivatives. Then the joint density for u and v, and that's what we want. So we know the joint density for x and y. We're trying to find the joint density for u and v. And it's defined like this. F of uv it's f of x, but we plug in, so that's the known density before, but we plug in this back transformation. And this is where we'd normally plug in x, but we're going to plug in this function of u and v, and then we're going to plug in this function of u and v for y. Then it's times the absolute value of the Jacobian. Now the Jacobian is it's actually of the inverse transformation, and that is this. So the first component, it's actually the determinant of what I'm getting ready to tell you. So it's the partial of x with respect to u, and the top right component is the partial of x with respect to v, and this partial of y with respect to u, partial of y with respect to v. So it's this determinant and then the absolute value of it. So let's do an example using this theorem. Let's let x and y be IID, uniform 1 to beta. So that means the joint distribution of x and y is just actually the product of these two densities, uniform densities, and that's what this is. So f of xy is 1 over beta minus 1 squared, and x and y can range freely from 1 to beta. Let's define u as x times y, and v is equal to y. Let's find the joint density of u and v. Now the inverse transformation is this. So y is actually just equal to v. And here, to solve for x, we divide by y, but y was v, so x is u over v. Now the Jacobian of this is the derivative of x with respect to u, so it's just 1 over v. Derivative of x with respect to v, so you get minus u over v squared. Derivative of y with respect to u, that's 0, and then we get derivative of y with respect to v is 1. Take the determinant, we get 1 over v. So now the joint density of u and v is this. It's f of u, v, is equal to f of x, and we plug in this quantity, u over v, for x, and then v for y. But notice that it's a uniform, so there's no u or v involved. So we just get this function back, the 1 over beta minus 1 squared. But the Jacobian of this transformation is 1 over v. And it's the absolute value of that. But v is always positive, so we can just have 1 over v. Now notice that v goes from 1 to beta, and u goes from 1 to beta squared. Or another way we can say it like this, since, let's go back up. Oh, where are we? Oh, here. So x goes from 1 to beta, so then we know u over v goes from 1 to beta. So there's a restriction there. And to me, it's easiest to see this in a plot of the domains. So that's what we do here. So the domain for x and y, they're both uniform 1 to beta. And so their joint density is this rectangle here, this square. And then when we transform it using this transformation, u is x times y and v is y. then we get this transformation. And the easiest way to do this, I have a whole playlist on transformations of random variables. We do univariate, bivariate, multivariate, and I go over in detail how to find these domains. But you essentially map a border. So you take this border and you can show that it has to map to this one, and then you can do that for the other three, and then you can find the domain. And this is it. And so this restriction here, u over v is between 1 and beta, and v is between 1 and beta, is exactly this. Now, to find a marginal density, so that's actually the next example, is find the marginal distribution of u. That means we have to integrate out v. So since this is a wonky domain, to integrate out v, we have to do it conditionally. So from 1 to beta, we integrate from this line to this line, and then from beta to beta squared, we integrate from this line to this line. And so there's two cases here. So this is the joint density of f of u and v, and we're integrating out from 1 to u. That's from 1 to u, and that's when u is from 1 to beta here. And then here we're integrating from this line, which is u over beta, to beta. And that's what we get here. Now, we take the antiderivatives and we get the log of v. And then we plug in the values, u and 1 and u over beta and beta. And we get this. So this is the density of u, f of u. That's it. And I do a R illustration at the very end of this video, which is kind of interesting. It matches so exactly to this. Now, to find the marginal distribution of v, and before we even start, let's go back up here. The problem is we have x and y are independent, identically distributed, uniform 1 to beta random variables. So that means y is a univariate uniform distribution from 1 to beta. And so look at this. If we want to find the density of v, it better be a uniform density from 1 to beta, right? Because that's exactly the way we defined it. But we're doing it, we found the joint distribution, and then we integrated out v to find the density of u, and then now we're going to integrate out u and find the density of v. So to integrate out u, we go from this line to this line from 1 to beta. And so let's scroll back down and look at it. So here's the joint density of u and v, and then we integrate from the line v and the line beta times v, and this is when v is between 1 and beta. And so there's no u here, so the antiderivative is just u, and then we plug in the limits of integration, and we get this 1 over beta minus 1, which is a uniform random variable from 1 to beta. And that's exactly what we expected to get. Now let's do a simulation of the density of u. Now I'm going to scroll back up one more time. And u is defined as the product of these two independent uniform random variables from 1 to beta. So what we do is we create these, we let beta be 3 because we have to pick a value, and let's do n of 100,000, and u is the product of these independent random uniform 1 to beta random variables. So that's u. So we create a histogram of it, and I say probability 2, so it estimates a density and limit from 0 to beta squared plus 1, so we have plenty of room. And then we plot the theoretical curves right on top. The log of x divided by beta minus 1 squared, the log of beta squared over x divided by beta 1 squared. And we put those in red, and look what we get. Let's see if it all fits on the curve, or on the, I'm going to go down one. And this is it. And so the gray rectangles are the simulated observation, and that's a histogram. And then the red is the theoretical curve that we calculated. And look how exact that is. That's just so amazing to me. Okay, well, we're right at 10 minutes, so I better end this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.